Welcome to the deep dive. If you're looking to get up to speed quickly but really thoroughly on what's happening in AI right now, you've come to the right place.
Yeah, there's just so much going on.
Totally. Today, we're diving deep into a really fascinating recent discussion. It covers basically everything from the nuts and bolts of models like DeepSeek and OpenAI,
Right? The architectures, the training,
all the way up to the global stage, the geopolitics of it all. We've got this detailed transcript, loads of insights on hardware, methods.
everything. And our mission today, really, is to pull out the most crucial bits, the surprising stuff from this source material.
Exactly. We want you to walk away feeling informed, maybe have a few aha moments, but without drowning in technical jargon.
Your shortcut to understanding what's really driving AI right now.
Okay, so let's kick things off. One of the first things that jumps out is, well, the naming. It's kind of chaotic, isn't it?
Oh, absolutely. Even OpenAI seems to admit it, with GPT-4o, then just o1, it's a lot.
And this discussion highlights DeepSeek, too. They've got their base V3 model, and then that leads to chat models and this reasoning model, R1.
Yeah, it's like trying to follow a new phone lineup every few months. But what's interesting with DeepSeek is that R1, the R is explicitly for reasoning.
Ah, okay. So they're signposting its purpose, positioning it near OpenAI's O1, maybe.
Seems like it, yeah.
Yeah.
They're putting a stake in the ground for reasoning capabilities.
Now, DeepSeek also seems to be getting buzz around open source. The transcript mentions this whole spectrum of openness, right? From wide open code and data.
Two things being much more locked down.
Right. So where does DeepSeek fit in? Are they like the good guys of open source here?
Well, they're definitely leaning towards the open end. Many see them as strong proponents. They released the weights for DeepSeek v3.
The weights? Okay, so the model's parameters.
Exactly. And under a really permissive license like MIT or very close to it.
But not the training code or the data itself.
Not fully, no. But they do publish pretty detailed technical papers and information about how they built it. That gives researchers a lot to work with.
I see. So by opening up the weights and sharing the technical details, what effect does that have?
Well, it definitely puts pressure on the other big players. Llama, OpenAI.
To be more transparent themselves.
Exactly. It kind of raises the bar for what open means in AI right now. It encourages more sharing, faster innovation, hopefully.
Okay, let's shift gears to the training. How do these reasoning models, like R1, actually learn to, well, reason? It sounds
Right.
way more complex than just feeding them text.
Oh, it is. R1 uses some really cutting-edge research techniques. And credit to them, they published a detailed paper on it.
So how can we break down that complexity?
You can kind of think about it in two buckets. First, how the model actually develops these reasoning skills that's like process emergence.
Oh.
And second, the specific math, the training losses, used to guide its learning.
Got it. So what are some of those key techniques?
Well, a fundamental one is still instruction tuning, sometimes called SFT, supervised fine-tuning.
That's where you show it good versus bad answers.
Yeah, precisely. You format the data so it learns the difference. Then you build on that with fine-tuning for human preferences using reward models, direct alignment.
And R1 goes even further, something about reinforcement learning.
Yes, RL with LLMs reinforcement learning with language models. That's a newer, very active area. OpenAI even has an API for it now.
How does that apply to reasoning specifically?
For models like R1, one really neat technique is using methods kind of like unit tests in software development.
Unit tests, how did that work?
You give the model multiple shots at answering a question, especially in domains where you know the right answer, like math or coding. You check its work.
Ah, so it learns from getting it right or wrong on things you can verify.
Exactly. It helps it improve its accuracy and reasoning in those structured domains.
That's clever. The transcript actually gave an example, right? Asking DeepSeek R1 for one truly novel insight about humans.
Yes, that was fascinating because the model, when pushed for novelty, seemed to almost challenge itself internally.
Really? Like what?
It talked about things like meta-emotion,
Mm.
feelings about your feelings.
Huh. Okay.
And this idea that society is built on shared hallucinations. Things like money, laws, they're concepts we all agree on that channel our instincts in useful ways. It was quite eloquent, actually.
Wow. Okay, that does sound like a leap. Now, the discussion also brought up mixture of experts or MOE. Sounds complex. Can you simplify that?
Sure. Think of it as a smart way to handle really massive AI models.
Okay.
In a standard model like Llama, they call it dense. Every single neuron, every parameter gets activated when it processes text.
Like turning on all the lights in a huge building just to read a book?
Kind of, yeah. Your brain doesn't work like that, right? When you see something, your visual cortex is busy, not necessarily the part doing math.
Right.
MOE is similar. For each little piece of text, each token, only a specific subset of the model's parameters the experts gets activated.
So what's the payoff? Why do that?
The big win is efficiency. Lower compute costs.
Yeah.
Both during the massive training process and when you're actually using the model doing inference.
Because you're only using a fraction of the model each time.
Exactly. DeepSeek's model, for instance, has over 600 billion parameters. That's way bigger than Llama 3's 405 billion. But because it's MOE, it can be more efficient to run.
So you can build bigger models that are still practical, overcoming scaling limits?
That's the idea. Bigger and more efficient.
And how does MOE fit into the transformer architecture we hear so much about?
Okay, so transformers have these attention parts that figure out what's important in the input. But they also have these big, dense neural network layers.
Right.
MOE is usually applied to those dense layers. They contain most of the model's parameters, its weights. MOE makes these layers sparse, only using some connections each time.
Instead of dense where everything is connected.
Precisely. That gives you the parameter efficiency. And remember, transformers are just giant neural nets, right? This is all part of the deep learning revolution, where generally bigger has meant better performance.
Got it. MOE helps scale up efficiently. The transcript also mentions some really low-level engineering stuff, like going below CUDA.
Yeah, it gets deep. To squeeze out every bit of performance during training, engineers sometimes work below NVIDIA's standard programming layer, CUDA.
Like what?
They talked about NCCL, that's NVIDIA's library for communication between GPUs during training. DeepSeek apparently did some custom work there.
Custom work on the communications.
Specifically on the routing mechanism within their MOE model, and tweaking things like the auxiliary loss, which helps balance the load across the different experts. It's a very detailed optimization.
Wow. What's the big picture reason for going that deep?
Well, it connects to this idea in deep learning called the bitter lesson.
The bitter lesson. Sounds ominous.
Maybe a little. The idea is basically that simple, scalable methods that just leverage more compute often win out in the long run over complex, hand-engineered features.
Okay, so how does DeepSeek's low-level stuff fit?
It suggests that their specific optimizations, tailored exactly to their model size and architecture, might actually perform better than using a more general library like NCCL, especially if they have limits on their total compute. It's about maximizing what you have.
The transcript even mentioned how stressful it is monitoring these huge training runs, watching the loss.
Oh, absolutely. It's high stakes. You're watching these graphs, hoping the loss goes down smoothly. Spikes happen. Sometimes it recovers. Sometimes you have to kill the run and restart from an earlier checkpoint. Huge waste of time and resources if it fails.
And they mentioned YOLO runs.
Yeah. Basically, large-scale experiments based more on intuition than proven theory. Like, let's just try this crazy hyperparameter combination and see what happens. Sometimes that's how breakthroughs happen.
Okay, let's pivot to the resources. The compute power, the GPUs, and the geopolitics. DeepSeek started in a hedge fund. That's unusual.
It is. Probably gave them early access to serious capital and maybe compute. They reportedly bought a lot of GPUs early on, maybe 10,000 back in 2021, possibly including things like H800s for their V3 pre-training.
Before the export controls really clamped down.
Seems likely. But it's important to remember the public numbers probably aren't their total research compute.
And how does their scale compare to, say, the big U.S. labs?
Still a big difference. The major U.S. players are talking hundreds of thousands of GPUs. Your DeepSeek, based on public info, is more in the tens of thousands.
Which brings us to those U.S. export controls on chips like the H800 and now this H20 chip for China.
Right. The controls are driven by concerns about AI's use, especially potential military applications, and this idea of military-civil fusion in China.
So the H20 is a restricted version.
Yeah, it's modified. Lower FLOPS, that's floating point operations per second, a measure of raw compute power. But interestingly, it seems to keep high interconnect bandwidth between chips, and maybe even has better memory specs than the H800 in some ways.
So it's not just strictly worse, it's different.
Exactly. It's designed to create a gap in certain capabilities, primarily the peak processing power for training the largest models, while still allowing some level of advanced AI development.
What's the thinking there if China can develop its own chips anyway?
The idea is to maintain a lead, to slow down progress in the most critical areas, even if you can't stop it completely, but it's a complex game.
What are the risks or downsides of these controls?
Well, there are potential long-term economic impacts of restricting high-tech trade, and some argue it might actually accelerate China's push for self-sufficiency in chip design and manufacturing down the line.
And lurking behind all this is the potential for AGI, right? Superintelligence.
That's definitely part of the subtext. The idea that truly powerful AI could offer decisive military or economic advantages fuels this competition.
The timelines for that are all over the place, though. The discussion mentioned Dario Amodei suggesting risks by 2026.
Yeah, that's on the fast trend. Others are more conservative, looking post-2030. And the transcript rightly points out the sheer cost and logistical hurdles of deploying AI at that hypothetical level. It's one thing to answer a query, another to perform complex autonomous tasks reliably.
The discussion also contrasted the US and China on building the infrastructure needed: data centers, power.
Right. China has incredible industrial capacity for construction. If they had unlimited access to the top chips, they could potentially build out data center capacity faster than the U.S.
But the US government has been focused on AI policy longer.
Arguably, yes, across both Trump and Biden administrations. You
Yeah.
see projects like Stargate getting attention. China's top-level government push seems maybe more recent, but they are putting serious subsidies into the sector now.
It feels like DeepSeek's progress might be acting as a sort of catalyst, pushing this Cold War mentality.
That's a sentiment you definitely pick up from the discussion. It adds urgency. And it all plays out against the backdrop of this vulnerable global semiconductor supply chain.
With the key R&D and manufacturing hubs in just a few places: Taiwan, US, South Korea.
Exactly. TSMC in Taiwan is hugely dominant in leading-edge manufacturing. Intel in the US, Samsung in South Korea are also critical. It's become highly concentrated.
And specialized, different fabs doing different things.
Right. The U.S. is trying to reshore some manufacturing, which is important.
Yeah.
But the cutting-edge R&D is just as vital.
Meanwhile, China's been investing heavily since 2015 to build its own domestic industry.
Yes, they've made huge strides, especially in older trailing-edge chips. They're nearly self-sufficient there. But for the leading-edge stuff, the GPUs needed for AI, they still lag, and that's precisely what the U.S. export controls target.
But those controls might push China faster in other semiconductor areas.
That's the potential unintended consequence, yeah. Ultimately, these controls really point towards a future where the global economy might be, well, more fragmented, especially in tech.
Okay, let's circle back to the models themselves. Performance, architecture. Comparing O1, Gemini. The transcript mentioned tokenomics of inference. What's key there?
Right. Tokenomics of inference is basically the cost of using a trained model. Training is expensive, but running queries also costs money.
How so?
A big factor in transformers is the KV cache. Think of it as the model's short-term memory for the current conversation.
Okay.
The longer the conversation, the more it needs to remember, and the memory needed grows really fast, quadratically with the context length.
So longer conversations become exponentially more memory hungry.
Pretty much. And that's a bottleneck, especially for these reasoning models that tend to generate much longer, more detailed outputs.
Because they're showing their work, their chain of thought.
Exactly. A chat model might give a short answer. A reasoning model like R1 or O1 might output tens of thousands of tokens explaining its thinking.
And that hits memory limits.
Yes, and it leads to this critical batch size problem. Because each user query needs so much memory, you can only serve a few users at the same time on the same hardware, which drives up the cost per user significantly.
But DeepSeek's R1 seems to have found ways around this. It hit #1 on the Chinese App Store, unlike Claude.
Apparently so. It suggests strong user adoption. Plus, it's open, MIT license, and the transcript highlights some architectural innovation in its attention mechanism specifically designed to reduce that memory pressure.
And the cost difference was huge.
Reportedly, yes.
Yeah.
Something like 27 times cheaper for inference than O1 was mentioned. That's a massive difference.
Wow. Even with other optimizations like flash attention out there.
Even considering those, yeah. DeepSeek seems remarkably cost-effective, especially given their funding history compared to the U.S. giants.
Why do you think they're so open releasing models like this?
Well, open sourcing is a great recruiting tool, for one. Attracts top talent.
Any other theories? The transcript mentioned speculation about financial motives.
Yeah, like timing releases to short NVIDIA stock or something. Seems pretty speculative, though. Their stated reasons are more about advancing the science. And it highlights the global nature of AI. If the U.S. restricts open source, others will fill the gap.
The conversation also got into aligning these models. making them behave, basically.
Right, a huge challenge. Training data has biases. It's hard to make a model forget things. So use post-training
Like
techniques.
system prompts, telling it how to behave.
That's one tool. But also RLHF reinforcement, learning from human feedback and preference tuning.
Yeah.
These don't just align the model, they actually improve its performance overall.
And constitutional AI, using AI to help align AI.
Yeah, using AI-generated preferences alongside human ones to guide the model. It's an active research area.
What was surprising was this DeepSeek R10 finding, reasoning emerging without explicit human preference data.
That was remarkable, yes. R10 was trained just using reinforcement learning on questions and answers rewarding correctness, and it started showing reasoning, even self-correction.
Without being told how humans prefer answers.
Exactly. This suggests some reasoning capability might be an emergent property of just learning to be accurate on complex tasks. The full R1 model does get human preference tuning later, but the zero version was telling.
Interesting. The discussion also compared different flavors of reasoning models, O1, O3 Mini, Gemini.
Right. Some early ones felt a bit narrow, maybe good at math or code, but less flexible. O1 was noted for being richer, more versatile.
And the amount of RL training affects how it expresses reasoning.
Seems so. Then they tested different models on a philosophical question. It showed their different strengths, answer quality, how clearly they laid out their thinking, that chain of thought.
OpenAI's O3 approach came up too, combining search with reasoning.
Yeah, stacking web search results on top of the chain of thought. And more complex search methods like Monte Carlo tree search are also possibilities to boost accuracy. It's about getting the model to do more work, essentially.
But that work costs money, right?
Mhm.
Especially for models like O1 Pro.
Definitely. Inference for these top reasoning models is expensive, but the trend is positive.
How so?
The cost of inference has plummeted over the last few years. Remember GPT-3 costs. Hardware gets better, optimizations improve. Costs might become less of a barrier over time.
Okay, final big topic. Infrastructure. These AI mega clusters, the scale sounds astronomical.
It really is unprecedented. We're talking about build-outs that are significantly increasing total U.S. data center power consumption.
Wow. And the GPT-4 YOLO run hardware seems tiny now by comparison?
Relatively speaking, yes.
Yeah.
What took maybe 25,000 GPUs then is dwarfed by today's plans. We're seeing OpenAI, Microsoft building massive sites, Meta expanding.
And xAI's cluster in Memphis, 200,000 GPUs.
That's the plan, using innovative power solutions too. There are diminishing returns, maybe, but efficiency still improves with scale, up to a point.
But it strains everything else. Networks, power grids.
Hugely. You see massive investments just in power infrastructure, like Amazon partnering with Talon Energy. And cooling, often overlooked, but critical. Water cooling right on the chips is becoming standard for density and efficiency.
The transcript mentioned Meta's fix for power spikes.
Yeah, the idle operator anecdote. Having someone literally do nothing to prevent sudden power surges, it just shows the insane amounts of power involved.
It's like a cluster measuring contest, as the transcript called it.
It kind of is. Everyone's racing to build bigger, faster.
And certain tasks just seem to soak up infinite compute, like math and code.
Things that are infinitely verifiable, yeah. They seem to benefit disproportionately from more scale. Plus, context lengths keep increasing, demanding more memory and different types of compute.
We also touched on Google's TPU approach versus NVIDIA's GPU dominance.
Right. Google's vertically integrated with TPUs optimized for their workloads. NVIDIA GPUs are more general purpose, dominating the broader market.
Which means models are often optimized for one or the other. Gemma on GPUs versus Llama on TPUs.
Exactly. Hardware-software co-design is key. And this plays into the cloud market too. AWS, Azure, Google Cloud. Their silicon strategies are a big part of their competitive positioning.
Are these dedicated AI labs actually making money yet? OpenAI, Anthropic?
Likely not, no. They're still heavily reliant on funding. Big players like Microsoft and Meta can absorb the costs because AI feeds into their existing profitable businesses.
But the future isn't necessarily winner-take-all.
Probably not. There are many ways to succeed with AI beyond just having the single best base model. Different niches, different applications.
What about agents? AI doing tasks autonomously?
Huge potential, but reliability is the massive hurdle. Getting those nines of reliability, like 99.999%, is incredibly hard in messy open environments.
Like self-driving cars or navigating the web?
Perfect examples. So we'll likely see humans in the loop, supervising or assisting AI workflows for a long time. Plus, access to training data is becoming a complex issue, paywalls, restrictions.
But AI for software engineering seems like a clearer win.
Absolutely.
Yeah.
Because code is verifiable, it works or it doesn't. That makes it ideal for AI assistance and automation. RLHF works well there too because programmers can easily judge if AI suggestions are good or bad.
So programmers should embrace AI supervisors.
Pretty much, it's becoming a powerful tool.
And the open source movement is still pushing forward, building on Llama, aiming for fully open stacks.
Definitely. Projects like Tulu, Olmo 2, trying to replicate top model performance with open code, open data, often on less compute. Defining open source is still tricky, though.
How so? Licenses, data transparency.
All of that. And weird 2S issues, like whether you can train on OpenAI's output, it's often
Is
ambiguous.
that actually enforce?
Sometimes. ByteDance apparently got caught. Smaller startups, maybe less so. There's this idea that allowing cross-pollination of ideas, even indirectly through model outputs, is ultimately good for progress, like talent moving between companies in Silicon Valley.
Okay, lastly, Stargate, this OpenAI Oracle mega project.
Right. It's huge, long-term, maybe a bit opaque. That $500 billion number, that's way down the road.
What's the reality now?
Phase one is more like $5–6 billion, mostly for servers. Oracle's building the infrastructure. It looks like a joint venture. OpenAI doesn't have $500 billion lying around. It just shows the scale needed for the next generation of AI.
So, wrapping up, the deep dive really covered the waterfront.
Yeah, from model details to the supply chain, the networking, the sheer complexity of making all these thousands of GPUs work together. It's an exciting and complicated time.
Well, this has been incredibly illuminating. We've gone from confusing model names right through to global strategy and billion-dollar infrastructure projects. Hopefully, we've managed to condense that complex discussion into something clear and useful.
We hope so. The aim was to give you those key insights, the surprising facts, and a real feel for the landscape without getting totally bogged down.
And hopefully you, our listener, feel you have a much clearer grasp now on the currents shaping AI's future.
Yeah, understanding the tech, the players, the stakes involved.
So here's a final thought to leave you with. With AI advancing this rapidly and these geopolitical and infrastructure pressures building, what are the truly unforeseen societal or economic shifts that might be lurking just over the horizon, maybe closer than we think, driven by everything we've talked about today?
That's the big question, isn't it? Definitely something worth pondering.